Hi, my name is Jim Leidel. I'd like to talk to you today about decarbonizing your church, your congregation's facilities. Consider this a roadmap, the beginning, maybe a guide to your vestry or your church to reduce their carbon footprint and save money along the way. We'll talk about how to finance it as well. This is done on behalf of the Creation Care Commission within the Diocese of Milwaukee. So I'm going to break this quite lengthy thing into 3 parts. I'm going to try to speed through this part 1. I'll be quick, so bear with me. But I'm going to post a YouTube with all the part 1, part 2, part 3. So part 2 is a case study, a hypothetical case study at a church that you can use as an example, a learning example. And then part 3 is talking in detail about each individual technology, solar and heat pumps and lots of fun things. So there are some tax credits out there, and this new the Inflation Reduction Act allows not-for-profits to take advantage of solar tax credits and different tax deductions and credits. So that is something new, and we'll talk about that. And we're going to talk about energy auditing and how to do an energy review of your facility and do some improvements, spend some money on some new equipment, and convert that units of energy, kilowatt hours, or CCF of gas into carbon, into how to talk about carbon reduction. So I'm a mechanical engineer. I've got degrees from Purdue and University of Michigan. I was born in Racine, Wisconsin. I did spend some time in Whitefish Bay and attended Christ Church when I was very young. My father's the late Reverend Bishop Ed Leidel, formerly also of Christ Church. And I've had a long background at working at a university in Michigan. I now work at a large gas and electric utility, DT Energy in Michigan. And I will try to fly through this. Feel free to read this if you'd like. I spent 16 years at the public university, Oakland University, just north of Detroit. Put in a LEED Platinum Green building and some cogeneration systems, large power generation, some solar. Studied wind, studied biomass boilers. And I left there because I knew these things with decarbonization and sustainable energy were coming, and I wanted to do more of that at the utility scale and help other customers beyond just my university. And these things happen slow. I thought it'd take 10, 20 years for these things to really take hold, but sometimes things happen a little faster. For instance, this is New York City looking down on Fifth Avenue, Easter morning in 1900, and there's this one there in the circle of these newfangled horseless carriages. The first one here in this picture, and about a decade later, this is 13 years later, just about a decade, can you find the horse? Sometimes these paradigm shifts happen real quickly. We're talking about electrifying the automotive fleet, the transportation industry. I don't think it's going to happen in a decade, but a lot of money needs to be spent, and a lot of technology changes, and a big paradigm shift is happening as well. But there is the horse. 13 years. What a fast change. So whether it's your vestry or a committee, or find some architects and engineering skills in your church, in your community, but maybe set some goals, set a vision. Do you want to lower your carbon footprint 50%, 80%, net zero? It's all possible. I want to show you that's all possible. It might take some time, maybe a couple phases, some money, but it's all possible. But it's going to start with an energy audit. You're going to want at least 12 or 24 months, maybe more. The more the better, to look at trends. But at least a minimum of 12 months of gas and electric bills. You look at your costs and your units of energy. And I want to show you how to convert those units of energy into carbon, CO2, carbon emissions. So your on-site fuel emissions, whether you have propane, natural gas, diesel fuel, whatever, on-site combustions where you burn it, combust it on-site. That's Scope 1 emissions. That's the terminology here we talk about. And Scope 2 is the utility company providing you electricity or some other energy source where they're burning a fuel remotely, far away. And that's going to be different per your local area. And I have some sources for that from the EPA. And then Scope 3, a much deeper dive. I won't get into that. Has to do with purchased goods, energy embodied in products you purchase, and transportation of your parishioners to and from church. Maybe things like building materials, for instance, building out of wood. That's a very sustainable natural product with very low carbon intensity, organic carbon, as opposed to concrete, very heavily dense with carbon. So concrete is big on Scope 3 emissions, where wood is very light. So those are way beyond the talk today, much beyond the scope of today's talk. So you need to look at your local grid intensity. I can help with that. And then look at your facility needs. Do you need new boilers, new windows? Do you have some problems? A new roof? I mean, there's energy impacts on a lot of these different things. So you can solve some problems, save some money, improve comfort, and then save carbon. So we'll talk about that. Then identify the technologies for your building, your site. Do you want to do solar? Do you want to do a power generator? Do you want to have backup power? Do you want to have new windows? I mean, all these different things are site specific for your facility, your church, your congregation, your budget. And maybe over time you phase multiple projects. So put a plan together. The idea is to make a plan, do a study, energy audit, and make a plan. That's the idea. So to reiterate and to drive home the Scope 1, Scope 2, Scope 1 emissions are things on your building site. Natural gas, typically, there's 117 pounds of CO2 produced for every million BTU, British thermal unit. A million BTU combusted, which is roughly an MCF. On your bill, you'll be probably a CCF or a MCF, 100 or 1,000 cubic feet. But a million BTU, 117 pounds of CO2. And then your local utility, electric-wise, will have a number that we'll have to research, and I'll show you that here shortly. That's the Scope 2. So here, the EPA, this website here, the EPA eGrid has these subregions, and Wisconsin is this RFCW. Here in Michigan, we're this kind of self-contained RFCM subregion, and each one has a different grid intensity. Mainly the coal is the biggest culprit. Natural gas has a lot of CO2, but coal has the most, by far the most. And then renewables and wind power, solar power, and natural gas is much lower. And in California has a lot of solar and natural gas. Ontario and New York have a lot of hydro. So it varies per region. So here's the numbers for right from the website. 1 megawatt is 1,000 kilowatt hours. So your utility bills will probably have dollars and kilowatt hours, most likely. So 1,000 kilowatt hours, a megawatt hour. That's a unit of energy. A megawatt is power. A megawatt hour is an energy term. And here's the data summarized here. So 2020 for Michigan, around 1,800, 1,700 per megawatt hour. But also, you might want to look into the future. So I've got a model looking to 2040. If Michigan DTE is saying they're going to be a 40% gas-fired base load, and they'll be 40% renewable by 2040, and 20% will be nuclear. That number, to me, I've calculated down here in the footnote, is 290 pounds CO2. I've got a consultant study here, a very reputable consultant, saying it's going to be a little bit higher, quite a bit higher. So it's not going to be zero. So if you want to say I'm going to go all electric, it's not going to go to zero for maybe 100 years or 60 years. It'll take a lot of time. Maybe on your site, your building, you could put all solar if you have the funds to do that, and the space, the roof, the land, and the solar access, clear sun with no shade. You could put solar to get your site to net zero, but the grid will not go to net zero carbon. So often you'll see people saying that, or hear people saying that you want to go all electric, electrify everything to decarbonize. But in the reality, in the Midwest, you're going to increase your carbon, maybe for the next 20 or 30 years. So in our lifetime, install a new boiler, install some new equipment, most likely you're going to want to look at natural gas and solar in a combination of things, not just all electric, because that'll actually increase your carbon. This isn't just a political statement, it's engineering that we're talking. So we're, once again, to reiterate, I'm going quickly here, but I'll make a YouTube video of part 1, part 2, part 3 combined. And you're going to start with the energy audit, look at units of energy, convert that to carbon dioxide with the concepts we were just talking about here. And then 117 pounds per million BTU for your natural gas, and then chart your path. Energy efficiency is number 1, number 2, number 3. I mean, pardon me, but that's the most important. It's not as exciting as solar and wind, but energy efficiency, lighting, heating, air conditioning, motors, schedules, lighting controls, schedules. Do you leave things on all the time? Outdoor lighting, indoor lighting. Let's do that first, and really look at your windows and your building envelope. A little bit more expensive. Maybe some insulation in the roof areas, but infiltration, drafts. It'll improve your comfort. It'll also improve your utility bills if you address that. And then maybe solar, as much as possible. I'm a big fan of solar, and not every church can do it, but it definitely will help. And it's also very visible and very much adds a lot of fun to the project, so people can see it. But then consider things like geothermal, on-site power, cogeneration or CHP, where you produce your own power from a natural gas generator and you recover the waste heat. That's a big technology. At the university I worked at, we put in a 5 megawatt large gas turbine in our central plant, and it lowered our carbon footprint over 40% and saved like $1.8 million per year. So it's a natural gas technology, but it's really, really effective in the Midwest. Consider renewable natural gas. You can actually get biogas or contract from utility programs. Often will bring you renewable natural gas, biological sources from landfills or dairy operations, especially in Wisconsin and Michigan. Then you can calculate your remaining, and if you want to meet your goal and you can't quite get there, you can actually purchase solar credits or carbon offsets, and that's something you can do as a payment or a transaction like a stock to get certificates to cover the rest. So that's how you get there. You can actually go to net zero with this, but it's all about balancing your usage, efficiency, and putting a project together, maybe more than one phase. Then paying for it, we have these solar credits. The Inflation Reduction Act has got 30% credit now available for Indian nations and K-12 schools and not-for-profits, including houses of worship. So you can actually get 30% credit for combined heat and power, geothermal or solar, and a 10% bonus, additional 10% for American-made product. And there's this really cool energy-efficient commercial building deduction. And that's a deduction, not a credit, but it's per square foot. So if you can reduce your energy usage by 50%, you get a $5 per square foot. I'll talk about the Christ Church, a 30,000 square foot church. If you can reduce by a certain percentage, you get that deduction passed through to your consultant or your contractor. And then they would then take that on deduction on their taxes. There's depreciation, some other things that could help out. So really you can knock out a fair bit of your project budget. Not all of it, but some of it with these things. And then I suggest financing the rest. And you design the financing, just like you engineer your technologies, you engineer your financing such that your payments are less than your savings. So you have a positive cash flow. That can be done. You can have an income from this whole project and not have any capital cost. You go to the bank and your payments on the bank note or a lease are less per month than your savings. That's the goal. I'm not going to read this, but this is talking about all these different tax credits. We're going to focus on the 179D and solar mainly, but there's also geothermal. There's credits for hydrogen, and big customers, not small customers, but big customers have this carbon capture opportunity where we can actually capture the CO2 in the exhaust from boilers and power generation. And one last honorable mention here. We'll talk more about each technology in part 3. If you want to go to the YouTube video, this is a community solar structure of a project. So basically, you could take 10, 20 parishioners together, and they could invest in a solar project and put the money in to get the capital cost to build it, put it on the ground or on the roof, and then execute a contract where either over time there's a lease agreement or a power purchase agreement, and the church then pays back the investors, and that way all the tax monies go to the investors. That's a pretty interesting way to do that, and this is not new. There's documents and things available for setting up this power purchase agreement for a community solar project on a church. Further information for deeper dive, I got a lot more coming in the technology section, but for planning and strategizing how to make this all work, this Energy Star has a good action workbook, an action guidebook here for congregations. A lot of states, Michigan, Wisconsin, I believe, and Minnesota have really good interfaith power and lights organizations. It started in California, and now a lot of states have their own little organizations. So consider that the end of part 1, and I'm going to move on to an example. This is a hypothetical example. I did the beginning of a walkthrough for an energy audit for Whitefish Bay Christ Church a couple of years ago. We never did the full energy audit, but I've applied some fictitious numbers to this to give us an example, just using this church as a backdrop, some photographs. And then in the end, I'll conclude with part 3. If you want to dig deeper into this opportunity here, there's a number of technologies, including solar and HVAC and boilers and on-site power generation that I'll discuss in detail. So let's jump right in. So this church has got some history since the 30s, beautiful old Gothic style with a new addition to make about 30,000 square feet total for the church, just north of Milwaukee here in Whitefish Bay. Looks like it was started back in 31. I copied this from the website. You can read this if you like, but I'm going to continue on. So it's been around a while. It's in a wooded area, suburban wooded area. Not a whole lot of opportunity for solar. I'll talk about that a little bit in the middle of the section here. There is a little bit of roof here next to this hatch that could offer some solar. But if you're really motivated, there's ways to put it on the side of the slate as well, but that's going to get into some serious architectural and aesthetic choices beyond just energy. It's a beautiful facility. There's a view from the south, so this beautiful big south-facing roof. If you wanted to get aggressive with solar, you could put some there, but that's not the best architectural location, but it is possible. Looking at the grounds from the street, there's now a big addition there. They love to have these summer events outside, very common. A beautiful little courtyard, stained glass in the church. Looking at the back of the kitchen area behind the church, in a little alleyway. And there's some asphalt roofing, but there's also some slate, I believe. And going through the walkthrough, I typically like to look at all the HVAC. It's great to have a full list of equipment. They don't always have that. But to make a list of all the equipment, like boilers, hot water heaters, air conditioning units. Lighting is important. I'm not going to dwell on lighting. It's a very meticulous, sometimes mundane thing to count all the light fixtures. So you really need to know every light fixture in the building. The gas meter here. These will be attached to each gas bill. So just to make sure you have all the gas meters and electric meters, so you know all the bills that you need to gather, make sure you don't miss anything. But the lighting could be done by a contractor, could be done by a youth group, could be done by a less skilled group of people, but it's basically counting each light fixture and then coming up with an estimate, if not the exact type of bulb. And then there's going to be a wattage for a fixture between the light bulb and the ballast. You're going to need both. So that's a bit of a job. It's also one of the best paybacks. Incandescent lighting is one of the least efficient things you'll find in the building. Now everything is going to go to LED. Even replacing fluorescence with LED is a good thing to do. Get rid of all the fluorescence and the mercury. Get rid of all the incandescence for sure. And then the maintenance, the life longevity of LED bulbs, especially in the high areas that are really hard to get to without a ladder or a lift. Once you do it, they might be there for 20 or 30 years. Get good quality bulbs there, because the ballast will wear out, and the power electronics might have an issue before the actual LED chips do. But anyway, lighting is important, and I'm not a lighting expert, but and then outdoor lighting as well. So parking lot lights and lights that are on all night long. So here's a review of the roof. There's a roof hatch. There's a smaller section here that's fairly unshaded, so you could get a fair amount of solar up there. There are some mounting racking style systems that don't penetrate the roof, but this is a little bit dicier of a discussion whether you'd want to put solar on this high slope. I did go up to the attic space and look up on that roof area, so we went up. Insulation, infiltration, those are probably things you're going to get a quote from a contractor. You're going to probably want to have a specialist give you a budget price for that, but that's often a very comfort-related issue as well. So you lose a lot of energy through infiltration, exfiltration, and old insulation. So that's a good idea to have a contractor give you a quote for that, or multiple contractors. I used to work for a university, and we always had to have multiple contractors and public bids. So this aggregate style roof could receive some solar. I wouldn't recommend doing penetrations to go through that, but there are ballasted systems that have weights on them. So you then need to think about only a few panels and the structural integrity, wind loads and wind blowing things off. There is no parapet there, so that's makes it a little bit dicey. But to the left here, there's a spot that could take a few panels. So I'm gonna put in 5 or 10 kilowatts for this project, just to have an example. But it's not the best, but you could put some here. There are some flat roof style that have adhesive mounts, and they're kind that penetrate the roof and go through to the wood or steel structure. But I would not recommend that here. You want to do no harm to the roof itself. It's obviously trying to keep the weather out, and it's not a very accessible location. Although it's not hard to get up there, but it's just not super accessible. It'd be nice to put a little something on the ground so that people can see it. I always like to have some solar that's visible. It's a really good, I hate to say hood ornament, but it's a visible feature of a project. If you have boilers and lighting and things that are not as obvious to the parishioners, a little bit of solar is a really good backstop to the whole project. It's a very visible, tangible thing to have. So hypothetically, using the church as just an example, you do a walkthrough and you gather the utility bills. That's the most important thing. So that's the first thing you do. And then you're going to convert all that energy, units of gas consumption and units of electrical consumption to carbon, the way we talked about in part 1. If you do 2, 3, 4 years of data, that's going to give you some trends. You'll see the extra heating in the winter. You'll see the extra air conditioning if you have it in the summer. So trends are fun to see, but 12 months is a minimum. You don't have to do more, but it's fun to do more. And then you look at the different project features that fits your site, fits your facility. I mean, do you have boilers and air conditioning units that are old and need updating? Do you have drafty areas? Do you have to do windows? Windows are very expensive, but they have an energy component. It means a long payback on things like boilers and chillers and windows, but they do have energy savings. And if you have to do it anyway, best to bundle it all together. My recommendation is not to just do the high payback lighting only and then quit, because that will help pay for the other things. So the lighting is usually the best payback, but bundling everything together is really where the power comes from to make a big project with a big impact. And then bundling is something I would definitely recommend. So this 179D tax incentive, we'll look at that. You'll need a consultant because the consultant must create an energy model. They actually have to have a third-party independent modeler, a professional engineer with certain software. Not too complicated, but it's a task that will cost a subcontract to that person. So an example, 30,000 square feet. Let's assume we have 15 cents a kilowatt hour and $6.50 per MCF. That's 1,000 cubic feet of unit consumption. Those are the utility unit costs. And then go through here, and I'm going to make up the consumption. So I'm going to say 8 kilowatt hours per square foot. So times 30,000 square feet. This is just an estimated electric usage. And if we're spending 15 cents a kilowatt hour, that's about $36,000 a year. Pretty heavy on the electric side compared to gas. I'm going to say 40,000 BTUs per square foot per year. These are annual numbers. That gives us 1.2 million or 1,200 million BTU, at just under $8,000. So that's my estimate. You're going to look at your actual bills. I'm just making this up for an example. You're going to go get your actual bills and make a spreadsheet to do that. If you have an engineer or architect or somebody technical in the congregation, that'd be great. You don't have to pay somebody to do that. I recommend you do it on your own. It just gives you an exercise on seeing the building for yourself. So this is a fictitious project that is very typical. Outdoor lighting, maybe a little high in dollar amount, but $10,000 for outdoor lighting, $20,000 for indoor. This is fully installed. These are contractor values, fully installed. And some of these things could be done by handymen in your congregation, or maybe you have contractors in your congregation. Not really difficult to change bulbs, but sometimes you'll have to change fixtures. It might be easier and better, more efficient to change out a whole fixture. But not always, just depends. That's why you have to go through and count all the lights and analyze it, maybe with a contractor, maybe with a lighting specialist, maybe not. And then I'm going to put in 10 kilowatts of solar PV on the roof. It's a little dicey if we can physically fit that much on this church, but just as an example, $30,000. There's a 30% tax credit there. If you're to buy American panels and American equipment, you can get a 10% bonus for a 40% tax credit. So insulation and caulking, I'm going to assume there's more insulation and some weatherization done by a specialist. of $20,000. And I'm going to not replace that boiler. We're going to talk about natural gas heat pumps. So this would be a unit that goes outside, and it's a second boiler, basically. It's a supplemental boiler, but it's going to get like 120 or 140% efficiency. So it's a heat pump, but it's a natural gas heat pump. We're going to put one in and add to it. So in the spring and fall, it's super efficient, and it'll be the base load unit. It's also very efficient in the dead of winter, but your existing boiler will just stay there and work less hard and last more years. Doesn't need to be replaced. So that's just a unique project I'll talk more about in part 3. And I'm going to say we're going to replace some office AC units and some units that were there. I didn't take pictures of them, but then engineering and project management. So contractors, designers, the people doing the 179D will have to have some design and drawings, and there'll be some profit for some contractors. So that's all. This is all installed, totally installed project, complete. And there's tax incentives that the designer will get that they will buy the project down. You'll have to have an agreement on how they're going to share that money. Basically, they'll pay their fees probably in the entirety. Maybe they'll give some back to the congregation in some fashion. You got to talk about that up front. But the solar tax credit is $10,000 for this example. The 179D, there'll be a letter executing that tax deduction for the congregation can be passed through to the designer because they're taxable, and a deduction of let's say they save 40%. We're going to assume all those pieces of the puzzle, all these items here, we're going to save 40% of your usage in the church, and they model that, and they're going to get that $4 per square foot. It's $2.50 up to $5 is the range you can get. So they get a $120,000 deduction, and then if their tax rate was 25%, that becomes a $30,000 credit to the designer or the contractor. So the $10,000 plus the $30,000, that's $40,000 incentive for the project. That turns into cash money for the installers off their taxes. And then there is a provision in the Inflation Reduction Act about getting cash payments for certain individuals. I have to research who that is, but talk to a tax official because I am not one, but this is how it works. So here is a wrap-up of this. The combined energy cost for the facility is about $43,000 a year. The energy savings is expected to be 40%. We're going to want to monitor that, of course, and verify that, but the savings per year is $17,000 with a $150,000 project cost, a net project cost to the church, and that's about an 8.5 year payback simple payback on your investment. So what I would recommend then is to not, you could have parishioners do a drive and collect money for that, but if you take out a loan for around 10 years, depending on the interest rate, 10, 11 years, maybe 12, depending on how high the interest rates have gone up lately, you could make it design the finances so that the payments on the lease or the loan, and you can lease some equipment or make a bank loan, the payments will be less than your savings. So you'll have a positive cash flow. Let me repeat that. I didn't make a bar chart, but you could show over time that your savings is greater than your payments that you're making to the bank. So that brings money to the church, no out-of-pocket money. You are taking on a loan for this, but that's the way to do it. So the incentives plus a bank loan could make this a zero cost and actually a positive benefit financially to the church, as well as all the energy savings and achieving your carbon goals. In this case, it's 40% energy reduction, and it could be 50+% carbon reduction for something like this. So that's the end of part 2. If you want to hang in there, I'm going to go through these individual technologies and wrap it up. So basically, you're going to look at your building and see what kind of energy conservation things would fit. Now, in the end here, I'm going to wrap up, talk about carbon offsets and renewable energy credits. Your utility company or a third party can sell you some offsets or some renewable attributes of electricity or other things out there that would cover some more carbon savings. And that's basically just a cash transaction. So it's a paper trail that says some other project somewhere else is producing some carbon savings or some renewable energy, and I'm going to take ownership of that on paper by paying a fee. That's legitimate, and it can be done to reduce your carbon footprint beyond your on-site solutions. Anyway, let's jump right into it. Once again, energy efficiency is the most important and usually the best payback. Lighting, number one. Lighting controls, occupancy controls, timers, things like that are helpful. They're not as quick as payback as some LED lighting technologies, but then HVAC controls, simple HVAC upgrades, sometimes motors, condensing units, air conditioning units. That's where you start. And then you want to get into the deeper energy efficiency things like potentially converting to a ground source heat pump. That's quite expensive, but it's one of the most efficient things you can do for heating air conditioning. It takes land and excavation, and it's a pretty involved project. But if you're super motivated, if you go solar with geothermal, that's pretty much the holy grail of energy efficiency. Unfortunately, converting to electric heat pumps will raise your carbon footprint in the Midwest. It'll be more carbon because of the coal in the grid that you're using to run your heat pumps. So that is not a carbon reduction solution on its own. But adding some solar to go with that would be helpful. CHP, combining power, putting on-site power generation with natural gas generators, that does reduce your carbon because you're producing natural gas efficient. Well, I'll show you more later. Then on-site renewables, solar, look at solar as much as possible. Parking lot canopies and building integrated, putting in a solar system somewhere else off-site, at a neighbor's house, or doing a community project off-site is a possibility. Solar thermal, wonderful. It's not as good as payback as you might think, but let's see here. And then off-site, you can put some solar or a wind system off-site and then fund that, and then take the renewable attributes of that, claim it for your church. That is possible. Then purchase renewable energy credits, carbon offsets. There are programs at your utility or other third parties to do that. That can get you all the way down to net zero if you so choose. And then just as an honorable mention, the natural gas grid. We will be putting blending hydrogen from renewable sources, green, clean hydrogen into the grid, 2%, 5%, maybe up to 20%. And there are renewable methane sources. Biogas can be upgraded and put in the gas grid. That is happening, and it will happen more and more. So don't discount the gas pipeline system as a delivery method for renewable energy. It's not just electric that will be renewable. It's 20 years behind, I think, than the electric industry, but it's coming. And then carbon capture, that's probably not going to happen in your church. I'll show you one example. But now we have the opportunity to capture carbon from the air, but most likely in your building it'll be done through your boiler exhaust or your flue gases. So there's technology to do that. The big companies have that available now. Actually, small ones too, but I'll show you one example. So for the 179, once again, lighting, HVAC, and building envelope are applicable to that, and you have to save at least 25%. So $2.50 to $5 per square foot for these three sectors of the project. Definitely worth looking at. You will need a consultant to help you with that, of course. So solar, getting cheaper and cheaper, but for roof-mounted solar, maybe $2 to $4 per kilowatt installed, depending on how difficult the racking is and how far you are from electrical, how complex. Ground mount systems can be down, closer to $1 per watt, or $1,000 per kilowatt, $1,500 per kilowatt. That's capacity, installed capacity. So then you have to multiply times the hours a day, hours of the year, and the capacity factor, which is maybe between 15 to 20% in the Midwest. So there's a math to get your kilowatt hour production, the yield of your solar electric. But that's the installed cost is typically based on the capacity of number of panels, basically. Very scalable. 5 panels, you can make a little ground mount system that's attractive, maybe into a flower array or some kind of an artistic installation on the ground where people can see it. But it's a very visible part of the project. Obviously, it needs to be in full shade, but it can be on a parking lot as a shade structure, or it can be on the ground, on the roof, it can be off-site. And I would not recommend batteries. Batteries are very expensive and they don't last forever, so they'll probably double the price of the project. But if it's a small job and you want to have some backup power, you could do that. But I would recommend a natural gas generator in lieu of batteries. It'll last longer, be cheaper to operate over time. Batteries will be a solution in the future as they get less expensive. So here's an interesting I think I mentioned this in part one, but community solar opportunity for a private investment. This is, instead of passing the tax credit to an installer, you could actually capture it yourself through a leasing mechanism or a power purchase agreement. There is a website. I'll put it in I forgot to put it here. There's a website. The Michigan Interfaith Power and Light have the documents for power purchase agreements and the financial legal templates available to do this. So basically, a number of people come together, they invest and fund the project with their investment dollars, and then the church would pay per energy use in the kilowatt hour over time back the money to the investors, and then they take the tax credits. So it's a nice way to do this, and a power purchase agreement is what I believe that forms. But look in the notes in the YouTube video, and I'll put a link to that. That's the Michigan Interfaith Power and Light. And there's a number of churches that have already done this. This is a great way to do it, and it can be done anywhere. You can put it off-site. You can have a host site that's using a lot of electricity at a business or at a large home, but it's fun to do at the church because that way people can see it. I'll show you a number of examples of solar, just because I think it's really one of the core things that you should be doing. Paybacks are not as good as some of the HVAC lighting. Number one, HVAC. Number two, solar and other things are down the road as far as payback, but very visible. It generates a lot of excitement. Obviously, it's a very, very tangible way to show the world what you're doing. Pennsylvania, a larger roof system, is a very shallow roof, a lot of roof space. So they had an opportunity to put it on the roof, although they could have put some on the ground as well. Nice part of the roof is it's out of the way. It's not going to get hit by rocks. It's not going to get damaged or vandalized very easily. Flat roofs are nice. But you are on a roof that has maintenance and has a limited lifespan. So these panels can last 20, 25, 30 years. They can be warranted for electrical output for 20 years. They last a long time. So you want to make sure your roof is repaired and in good standing before you put the solar on it. And that can be a challenge if you have an old roof. You want to repair the roof first because these panels are going to be there a while. You'll see here the ballasted style, little concrete blocks. So this has got a parapet, and in an urban environment like this, you're not going to see most likely any major wind events that would disturb these. But the ballasts, these can take high winds, and you see they're relatively shallow inclination. So that's a great solution. That's the most common solution for commercial roofing. Here's an interesting cross set up in a little country church. And this is on a tiled surface, so this is possible. This is similar to Christ Church, so it is possible to do this. Obviously, the aesthetic choice and the architectural issues are going to be a big part of the discussion. This is a tile system and a roof in the UK. So this is definitely a slate tile system with a special product to be integrated directly into the roof. And there's one made in Michigan. I live in Rochester Hills, Michigan. This company here, the Allen Brothers, it's called Luma Roof. Their product is called Luma. They have a separate company that makes this beautiful Bermuda roof with these tiles built in. And I have a little section built on my roof. In the last couple months here, I'm working on a project. It's a beautiful solution. So there's a lot of different stuff like this, but I shout out to the Luma guys. They make a beautiful product. This is my roof. It's a brand new asphalt shingled roof, and I have the color contrast there intentionally to see that on my roof. So I got 4 kilowatts. I also have a little micro CHP, little engine generator, and a battery system for a hybrid house, a design that's unique in a demonstration. Here's a geothermal system. This is like a district system for multiple buildings. You don't necessarily need a combined heat and power, but that's just for backup power. But the ground loop can be horizontal. It can attach to a river or a body of a lake or body of water. But the vertical boreholes are the least amount of land. But geothermal is very efficient. But you're using electricity, so it's an electric system. And you got to look at the math of your grid carbon intensity because you might be raising your carbon footprint. But much more efficient than air source heat pumps. Air source heat pumps are an option as well. Basically, that's an air conditioner that's running backwards or forward. It's reversible. But this is a heat pump, reversible heat pump that uses the ground and the source of energy in the ground as a heat sink or a heat source. Oops. So this is a explanation of how heat pumps work. You hear air conditioner in your house, on your refrigerator in your house is a heat pump. It could be a unidirectional, one-way heat pump, like your air conditioner or your refrigerator, where it's pumping heat out of an area into the outdoor air with an electric compressor and refrigeration. Or it can be reversible and have the heat go either direction, and that's a heat pump. So here in the one season, we're AC cooling mode, and then we reverse it into the heating operation, where we're pulling heat from the air outside, or with the geothermal, we're pulling it from the ground. And the ground is always in the 50, 60 degree range, depending on where you are. In Wisconsin, you're probably going to have 50s or low 50s in your ground temperature. So they designed the ground to always be able to pull that heat out of the ground. It's not as hot as summer day, but it's never that cold. How about a gas heat pump? Well, if you have a heat pump that's working with natural gas as your fuel source, yes, you can have a boiler or a device, a heat pump that's 120 to 140% efficient. There are products out there. This is a Rober unit. I can show you another YouTube video of a commercial or a residential property with Rober. This is an absorption cycle. There are engine-driven units that run a refrigeration cycle from an engine, a natural gas engine. Yanmar, Eisen, and others. Some foreign product. This is it was an American product. I think that was bought by an Italian company, Rober. But these are very effective, and they produce heating at about 140% efficiency. This company also produces a dual unit that can make cooling or heating. So they can be a heat and cooling option off of natural gas. And all the different types of heat pumps are shown here. So they can have electric source or gas source. I'm just showing you this because people don't always realize you can have a gas-driven heat pump. Often much more affordable, and definitely a solution if you want to have the reliable winter heating season with natural gas, but add efficiency as well, and the heat pump will do that for you. It's something worth looking at. Don't have to replace your boiler. It could be supplemental and go side by side with the boiler, or it could be installed outside and piped into your hot water loop. On-site power is available in many different sizes. I'm putting a little 1 kilowatt unit in my house from a company called Eisen, a Toyota Group company. This one is made in Wisconsin. It's about 4.7 kilowatts, made in a company called EcoPower. I think they've changed the name. Yeah, they've changed the name. I think it's Axiom. They're south of Milwaukee, about an hour, 45 minutes southwest. It was made by York and Battelle, and it was a Briggs & Stratton project for a heat pump. And the company that was manufacturing it kept going after the project ended, and it was called EcoPower for a number of years. But I believe it's Axiom. But there's many sizes: 50 kilowatts, 20 kilowatts. Gridiron Energy is a new one in Texas. Houston, Texas. I can hook you up with a lot of different options here. So this will provide you backup power if designed to do so, and it can provide heat and power. Here's a 20 kilowatt unit from Lochinvar. A.O. Smith, Wisconsin-based A.O. Smith, purchased Lochinvar, and now this one they're selling as a tank. It's a 20 kilowatt unit. So what is CHP, or cogeneration? The old name was cogeneration. So the grid produces power from coal, nuclear, natural gas, and the coal is the culprit for the vast majority of the CO2. And that heat that's generated in a power plant is then thrown out to a lake or a cooling tower, just like your car engine. You throw all that heat out to the radiator. So the heat engines in the United States, we're throwing away about 60% of our energy from heat engines: cars, trains, planes, automobiles, and power plants. Then at your church or your home, you're using a boiler or furnace to make the heat. Well, what if you would use this waste heat? That's what CHP does. So you're using a much lower CO2 intense fuel. So the carbon savings comes from the efficiency of recapturing this heat and the lower methane, the natural gas carbon footprint is much lower than your grid. Now that'll change over time as the grid becomes more and more coal-free. It might take 10, 20, 30 years, depending on where you are. I don't think Wisconsin is going to be zero coal anytime soon. But I'm speaking about Wisconsin because this is focused on a Wisconsin opportunity. But it's true for the whole Midwest, as you see in part 1. So once again, the natural gas grid will soon be receiving some amount of hydrogen and it already has some renewable natural gas. There's credits for renewable natural gas, so they're going to the transportation market on paper, but the renewable gas from dairies and landfills, it gets cleaned up, and it's called RNG, renewable natural gas, that gets pumped into the grid. So you already have some small percentage in the gas pipeline now, today, as we speak, and that'll increase in quantity over time. And there's ways to contract to get more of that as well from third parties, or maybe your utility. Just to drive home, here's a chart showing the different CO2 output, the carbon intensity of different fuels. Natural gas is the lowest carbon footprint of any hydrocarbon. Being CH4, it's got one carbon molecule, and it produces the least amount of carbon dioxide when combusted. So when you combust natural gas, you get water vapor. That's the steam and the plume of white steam you see coming out of your exhaust, and CO2. RNG, Wisconsin's got a lot of dairy going on, and some of these sites actually will clean up that anaerobic digester output, which is not pure methane, but it's a high methane output from these digesters, and it can be from a landfill, can be from a future gasification site that uses a woody product or ag waste, or wastewater treatment plants. A lot of material, any organic material out there can be made into methane. And if you clean up the gas and make it to specifications that the utility company allows it to be injected into the grid, that's what they do. And that's being done more and more and more. And it's a big part of their future of decarbonization, because we have this huge infrastructure of natural gas. And in northern climates, it's really not feasible to go all electric for cars and buildings. So this plus hydrogen, plus efficiency, and all these other measures that will do the job. Some terminology: the biogas coming right off let's say the anaerobic digester is producing 50% or 80% methane, depending on the type of digester. Cleaning it up, you have this RNG. I like to just call it renewable gas. Some other colleagues in the industry call it renewable gas, and that can cover synthesized green methane from a synthetic source, or hydrogen, or all these other gases, and we'll be blending them into the gas grid. For the chemists among you, when you have CH4 combusted, you use oxygen out of the atmosphere, and you produce 117 pounds of CO2, as we mentioned, and then a lot of water vapor. So there's a lot of water vapor that's produced, and this is for 1 MCF of natural gas. But CO2 is mostly oxygen. There's actually methods to make carbon black and to split that out when you make hydrogen and have solid carbon. But for carbon capture, we're going to have a lot of CO2 captured from big companies, and that'll become more and more economical, and maybe smaller systems will be available that are prime time and available commercially. There's one I'll show you in a moment, but this is a chemical process where you have an amine solution, basically a solution that sucks the CO2 out of a tower or a device, where you pass the gases through, and you bubble or somehow pass this solution through, and it sucks in the CO2, and then you heat or cook the liquid elsewhere in another part of it, and drive off the CO2 to be captured. But then it has to be compressed and liquefied and transported or piped. So there's a big discussion about what you're going to do with it once you have it. And if everybody's doing it, we're going to have billions of tons of CO2. One device that out of Canada that does that, it uses a potassium hydroxide solution, and it's got a different method. It's a process that needs bags and bags of this KOH, potassium hydroxide, but it makes a pearl ash. It makes a solid precipitate, a solid pearl ash substance. And you can put this in a church. This is a smaller unit that could potentially be viable for a smaller installation like a church. And this then is collected and sold off, and they use it. You can make soap out of it. It's industrial chemical that has a value. So that's one option. Carbon offsets, if you really want to go deeper, then you can with your own equipment on site. I didn't delete this here. This DT gas, we have a carbon offset program here in Michigan. It's available to anybody because it's goes beyond our borders, but there's lots of programs like that. This slide from another presentation. Renewable energy credits from solar and wind projects are available out there for purchase from your utility or other third parties. And carbon offsets, renewable natural gas programs where you can purchase on paper some RNG. So all these are options available that go beyond physical technologies that you install on your site, but then you just pay cash for these programs. So for a deeper dive, there's a lot of good sources. This, I mentioned it before, this action guide for congregations goes through the whole project development steps. It's really nice. These faith-based organizations, I'm going to give a link for the Michigan Interfaith Power and Light website. MIPOL, I think. Is it MIPOL is the acronym? But it's here, listed here. They've got that great solar, third-party solar power purchase agreement, all the forms and documents there on their solar page. So I'll provide a link to that. Learning more about individual technologies, feel free to go to any of these websites: combined heat and power, renewable natural gas, heat pumps, carbon offsets, solar, a lot of good stuff. So I hope this is enough to get you started. I know it's a bit long, but there's a lot of options for you. And I hope you can create a committee or a group that wants to investigate further. But once again, you start with your energy audit, convert that data into units of carbon as best you can, and then see what's available for your church. I hope you had fun, and I'll put my contact information in the YouTube footnotes. Thank you much.